These are the first notes on solutions, a new unit that we are now starting. Solutions is a major area of chemistry because many chemicals come in the form of solutions. Many chemical reactions that we deal with in the chem lab are in the form of solutions. A lot of them are aqueous, and there's even other solutions. Some you may not even have thought of. Until you understand what a solution is, you might not realize how many solutions you've actually already been dealing with. Science is basically trying to understand the world around us. The world around us is made up of a lot of phenomena. That's the plural of the word phenomenon. So in my phenomenal box this time, I've got the Earth's ocean. We live in Southern California. Well, we are surrounded, well, not surrounded, but on one side, we've got the Pacific Ocean. The Pacific Ocean is just the largest part of the Earth's ocean. They're all really interconnected. And the great thing about the ocean is it is the largest solution that you're probably ever going to come across. So when we study solutions, remember it has an application towards understanding the oceans of the world. Up until now, in chemistry, we have been dealing with pure chemicals. We've been talking about an individual chemical and the way it behaves, because if you isolate it, it's easier to understand it. And then we started talking about how one pure chemical will react with another pure chemical and what they will produce in a chemical reaction. But in the real world, it is much more likely that you will encounter chemicals in mixtures rather than pure. And so in this unit, we are going to be understanding solutions, which is a particular type of mixture. So what is a solution? Here's the definition. A solution is a mixture of two or more chemicals that is stable and homogeneous. Now, normally in high school chemistry, we deal with two chemicals at a time, two that are mixed together. That makes things a little easier to understand. And then only toward the very end will we be dealing with some combinations of three. So a homogeneous liquid mixture, which is usually how we find solutions, has one main component as well as one or more additional ingredients that are present in smaller amounts. So there's two chemicals, but usually one of them makes up more of it and the other one makes up less of it. We'll be talking about what those are called in a moment. Let me just point out that solutions are all around us. As I mentioned, the ocean is a solution, but there's many more solutions that you may have overlooked. You're breathing a solution, you might be wearing a solution on your finger. So solutions are all around us, and we are now going to begin to understand them. Here is an example of a solution. This is like a poster child solution that I made. A beautiful solution. The way we think about them is normally in liquid form. Look, it comes right up to that 1,000 milliliter line. The bottom of the meniscus is resting on it. That's a liter, by the way. So a liter of blue solution, beautiful. That solution has two components. One of them makes up less of it, one of them makes up more of it. So remember, a solution is a mixture of two or more chemicals that is stable and homogeneous. If you have to picture something, there you go. That's the image I would like you to have in your head for a solution. When we talk about the word homogeneous and heterogeneous, let me just mention, first of all, that there's more than one way to pronounce each of those words. You may have heard them pronounced other ways. For example, you can say homogeneous and heterogeneous with more syllables. The way I pronounce them with my accent is homogeneous and heterogeneous. I have a few things about my accent that are unique. For example, the way I pronounce electricity. I think it's almost like onomatopoeia, the way I pronounce it, and I like to stick with that. Even though I do realize that it's spelled with a C, not a Z, I pronounce it as if it's zapping you. So homogeneous mixtures on the left are good mixtures. The word homogeneous means it's all the same. It's all the same throughout. That means they're mixed really, really well. Heterogeneous on the right, notice it's not very well mixed. That's not a good mixture because it is different in different places. Notice that the chemical on the top, probably oil, is completely separated from the chemical in the middle, probably water, and the chemical on the bottom, okay, of unknown origin. So there's 3 different chemicals there, and they're not mixed very well. That's a heterogeneous mixture. So remember, solutions have to be homogeneous, like the one on the left. They cannot be heterogeneous, like the one on the right. That would not be a solution. But that is a mixture. It's got more than one chemical present. Got it? When you have fresh water, or let's say distilled water, pure water, it only has water molecules, H2O. That is only one chemical. Well, that's not a mixture then. So fresh water is not a solution. Why? Because it only has one chemical. Asterisk, I will cover this later that I'm actually technically lying to you, but remember, this will be explained later, so it's a little white lie. On the other hand, we've got salt water. Salt water may appear to contain 3 chemicals if you think about it. It's got water molecules, H2O. It's got sodium ions, Na+, and it's got chloride ions, Cl-. But the way chemists think about it is actually that you mix sodium chloride, NaCl, with water, H2O, to make this solution. So this is considered a solution of 2 chemicals, even though the ions do split up, they dissociate. So salt water, which again, that's what the ocean is made of, salt water, is a solution of sodium chloride in water. And we'll examine that a little more later on. Let me just mention right now that in solutions chemistry, there's a big issue with the vocabulary words. Most of the words begin with SOL. The word solution, the word that we're about to see here, and many that we will see later. So you really have to be able to tell the difference between all of these terms that all begin with the same 3 letters. So please, please be very careful in that respect. The 2 words that we're dealing with here are solute and solvent. The primary ingredient in a solution, the one that makes up most of that solution, is called the solvent. The other ingredient that makes up less of the solution, when it is dissolved in the primary one, is called the solute. Now notice the word solute sounds as if it has a Y in it right before the U. Solute, that's how we pronounce it. So solvent and solute are 2 terms you really need to be familiar with if you're going to get anywhere understanding solutions. When we mix 2 chemicals, always one of them is more than the other. Oftentimes, the solvent is way more, let's say 80, 90, 99% of the solution, whereas the solute is much less, like 10% of the solution or 1%. That's more typical. Now, a lot of the solutions that we make use water, and often there is way more water than the other chemical, making water the, which one? Water is the most common solvent. If you remember that water is a solvent, that will really go a long way to help you keep the 2 terms straight. Water is very, very typically the solvent. When water is the solvent, it is called an aqueous solution. So most of our solutions we're going to be dealing with are going to be aqueous solutions. That comes from the Latin word aqua, which means water. So aqueous just means a water-based solution. Water is very unique because so many substances can dissolve in it. I'll get to that on the next one, on the next slide. But there are other kinds of solutions. They're not always liquid. For example, air, the air you're breathing, is a solution made of gases. It's not just one chemical, right? It's more than one, and they're mixed and they stay together. That is a solution. Another example of a solution is brass, bronze, steel. Those are metal solutions made of multiple metals combined and that's a solid state solution. So you can have solutions that are gas, we'll talk about that later. You can have solutions that are solid, we'll talk about that later as well. But for the most part, like the stereotype, solutions are going to be in liquid form, and most of those will be aqueous. Water has a nickname. Water is the universal solvent. Now, that ties in one theme park in Southern California, Universal Studios. But what about the other one, or one of the other ones? Well, look at the shape of the water molecule, and look at Mickey Mouse's head. Interesting that the shape of a water molecule is pretty much like a decapitated Mickey Mouse head. So what a molecule. Water, water everywhere. It's ubiquitous. Now, that's a quote from the Rime of the Ancient Mariner, if you want to look it up. Water is known for dissolving things. It'll dissolve salts, bases, acids, polar molecules. It's like I'm selling water, like in a commercial. People do sell water. Think of water bottles, water purifiers. And the density is number one. So number one, I mean 1 gram per milliliter. And these make what we call aqueous solutions. So notice I have it sponsored by Aqueous Solutions Limited. There's a few disclaimers at the bottom, like in any commercial. Well, you have to have those. But water is a really great solvent. It will dissolve more chemicals than anything else. So it's a pretty good name, but it's a bit of an exaggeration. Just like many commercials, the claims made are usually exaggerated somewhat. You know, universal implies it'll dissolve anything in the universe, but water will not dissolve anything in the universe, as we will see. So water is a great solvent, and if you remember this little nickname, the universal solvent, if you remember that, then you'll never get confused about what a solvent is. Which one is which, solvent and solute. Water, if you see it in a solution, is most often, almost always, we will see exceptions, but almost always the solvent. In a solution, the solute is less and the solvent is more. The solute is less, the solvent is more. I put the solute on top and the solvent on bottom for a reason, because when we set up equations, well, of course, we're going to get quantitative at some point. Come on, this is chemistry. When we get quantitative, the solute finds itself on the top of the fraction, and the solvent finds itself on the bottom in the denominator, as you will see very soon. An example of a solution that you might have heard of is an alcohol solution. If you mix ethanol with water, well, it turns out they will dissolve. They'll make a solution. By the way, not every two chemicals will. Some chemicals are what we call insoluble. We'll get to that a little bit later. But if they do make a solution, well then, you've got something that is stable and homogeneous. Look at a 14-karat gold ring. Remember, 14-karat gold is actually a gold-silver alloy. You can combine them when they are both molten, and then once they mix and they solidify, they cool off and solidify, they will stay together. Notice on that 14-karat gold ring, you don't see any little spots or lines of silver. The silver is evenly mixed. That's homogeneous. So that little snapshot in that circle could be found anywhere on the ring. It's the same mixture. You wouldn't find any places on that ring where there was more silver and less gold. It's evenly distributed. That's what we mean by homogeneous. Also, in the ethanol water mixture on the left, you wouldn't find any place in that beaker where you have more ethanol and less water. They would be evenly mixed. That's what homogeneous means. And to be a solution, they have to be stable. They have to stay together. So that ring isn't going to suddenly separate into gold on one side and silver on the other, and that solution isn't going to suddenly separate. There is a way to do it, but if you keep it in the beaker under normal conditions, it will stay together in a solution. So now we know that a solution is a mixture of two or more chemicals that is stable and homogeneous. You should have understood everything I just said, and the solvent is more of the solution, the solute is less. That's where we are right now. So you should understand what I just said. And let me add that to my little poster. On the right, notice a solution solute is less, solvent is more. We'll be adding more things to this poster as we go on. So these are the things I'm expecting you to know by now. However, mixtures don't have to be solutions. Mixtures can also be heterogeneous because not every two chemicals will mix. We'll talk about the reasons later, but some chemicals just don't make a solution together. They're insoluble. Well, if that happens, you might get a couple of different situations. One of them is what we call a suspension. A suspension is a mixture in which particles, usually larger particles, are pretty much evenly dispersed, pretty much looking homogeneous, but if you wait, the particles may remain mixed while the liquid is being stirred, but later they will gradually settle down to the bottom. And if they settle to the bottom, well, that's not stable. Well, that was never a solution to begin with. So suspensions are a little bit deceptive. On a macroscopic scale, when you look at them, they might appear to be solutions momentarily, but if you wait, which we always should do in chemistry, give it at least 5 minutes, that's what I say, the rule of thumb, and after 5 minutes, if it begins to separate out, well, that was never a solution to begin with. Another one is called a colloid. You might not have heard that word before. Colloids are often emulsions, if you've heard that word. It's a heterogeneous mixture where the particles never settle. Well, the reason they never settle is a little complicated. We'll be getting to that in one of our labs a little bit later. But basically, a colloid is when you have a big clump floating around in another, what would otherwise be called the solvent. We don't normally call it the solvent in chemistry because it's not a solvent unless it's part of a solution. But in the wide world, they do sometimes refer to it as a solvent. For example, paint is a colloid. Paint is a colloid with large clumps of material in it. And if you smear it out on the wall, well, the part that would have been, let's say, the solvent evaporates, and all that you have left behind was the clumps that were inside of it. Not really a solute. And another example of a colloid is milk. Milk has large clumps of fat floating around inside of the solvent, inside of the water. And the way that that works is a little complicated. We'll talk about that later. So if you look on a microscopic level, it's not homogeneous. So colloids are not solutions because they're not homogeneous, they're heterogeneous. And suspensions are not solutions because they are not stable. A good example of a suspension is muddy water. If you take some mud or just some fine-grained dirt, stir it up in the water, well, that looks pretty homogeneous at a glance. But on a microscopic level, on the right, you can see that those large clumps are not going to be able to float around in the water forever. They will gradually rain down and settle on the bottom. And once that has happened, well, that is clearly heterogeneous. You clearly have one chemical on the bottom, which would be, let's say, the silicates, the sand particles, the mud particles, and the water is mostly above that. So that is not a solution at the bottom, clearly. That means it was never a solution, even at the top, before settling. So be careful. If you have a suspension, it could be deceptive for a moment, but usually 5 minutes will show you that at least it begins to settle. If not fully settling in 5 minutes, you will at least begin to see it settle out. So here are the definitions for a solution, a stable homogeneous mixture. Again, it's two or more chemicals. A suspension is a mixture of two chemicals that appears uniform when being stirred, but it separates quickly after stirring. Another example would be in a river where there's enough agitation from the flow of the river to keep various silicates suspended in water, but actually silicates are not soluble in water, so they will eventually settle out on the riverbed. Then there is a colloid. A colloid is a mixture in which the small particles or clumps are suspended throughout. It doesn't separate. You can homogenize it, so to speak, to get rid of it, but colloids are tricky. One way to detect a colloid is with a laser beam. If you shine a laser beam through a liquid that appears to be a solution, but you can see the scattering will be due to the clumps of the colloid. That's one way to tell a colloid. If you shine a laser through a solution and you see a large amount of scattering. The tricky thing is that you will also sometimes see a little scattering in a solution if it has any fine-grained particles mixed in. Let's say if your solution isn't perfect, if it has any sort of other materials mixed in with it that you weren't accounting for. So I will just say for a colloid, if you see a very obvious large amount of scattering, that gives it away. So try to think of 2 examples of each. I think I've given at least one example of a suspension. I may have already given you 2 examples of colloids, and we will see lots of examples of solutions. I think I gave you more than 2 in these notes. Just be prepared, make sure you can think of at least 2 examples if that comes up. Those were notes on solutions part 1. They were very, very qualitative. Well, we will be getting quantitative in part 2. We will learn more about solutions in our next notes.